So today we're going to talk about soil texture and other soil physical properties. I think texture last time we did talk a little bit. Did I? The soil triangle. Did I cover that previously?
Yes.
I did. So good. Okay. So it should be fast then. Now, texture is part of the things that I want to cover. Apart from that, is soil particle density and also soil bulk density. Look similar, but they're actually quite different. And then some other related physical properties as well, like soil porosity, aeration, and then the others such as soil color, consistency, and also soil temperature. So these are what we call physical properties that is measured physically using very simple technique. And these are the parameters that will not going to involve any chemical changes of the soil, or at least the physical part is what they want to determine. Okay, so let's start with soil structure. Now, when we talk, okay, what is the difference between structure and also texture? Last time we did cover about soil texture, like loam, sandy soil, clayey soil. Okay, now last time when we talk about soil texture, it is closely affected by the composition of three components in the mineral phase. If you still remember, sand, silt, and clay, different percentage of these three components were going to dictate how the texture will going to feel like. Now it's the same with texture, structure, in which due to the different particle sizes and also their adhesion with water, they're going to have a very different ability to absorb moisture, and also that will going to affect how the texture will going to feels like. Now that also is quite similar with structure as well. So if you look at the diagrams, as you can see right here, there are two images that reflect good soil structure and bad soil structure. So what is the difference? Okay. The difference is, for a good soil structure, it will going to allow air and also moisture to pass through freely. Okay. Now you're probably going to ask me, you're probably going to think right now, sand probably have good soil structure, but the answer is probably not so, because when we say when I say air and water pass through freely, doesn't mean that pass through quickly. You see, sand is not really a good soil because usually sand does not retain water. You have water, it passes through quickly, and it cannot retain water in the soil, at least in sandy soil. Now, those are not what I mean in terms of good soil structure. Okay, so for a soil that is considered good in structure, they must be able to let air and water to pass through freely, but not too quickly, because a good soil also depends on how well they can retain moisture. Okay. Now, if you look at the other side, bad structure, it is said to be like air and water circulate badly. Now, what kind of soil that we're going to have this kind of condition? Straight away you're probably going to think clay, right? Because clay, if you remember, they are so sticky that there's no air or room that separates these clay particles, and they are usually very sticky and wet. Now, being wet itself is one thing that is an indication that the water do not circulate so well, and they are like staying around. They're ponding and they stick around. So you can already see like the difference here between these two structure. Now, when I say sand versus clay, now if the tendency of bad soil structure is associated with clay, whereas a good soil structure is associated with slightly sandy and more airy soil, soil structure is actually closely related to texture. If you can determine the texture, you can also like kind of see the structure as well. Yeah. By the way, now if I say sand is not really having a good soil structure, then what is the suitable soil that with good structure and have the ability to retain moisture? The answer is any soil with high organic content. You see, now after this, probably next week when we go to new chapter that talks about soil chemical properties and soil organic matter. At that time, I'm going to talk about how the soil organic matter will going to give you a good structure with interaction with soil particles. So in this case, you can say that a good soil structure are those that usually having high organic matter, and because of that, they can allow air to pass through. So don't worry about it. I'm going to explain probably next week regarding the details about organic soil with good soil structure. Okay, now as what I have told you earlier, good soil structure influences water movement, in which water can pass through, but not quickly, but not too quickly, and they can still retain moisture. Uh, Heat transfer. Now, what do they mean about heat transfer here is that for any soil particles, they were going to conduct heat or absorb heat from solar energy. So sunlight, once they have like irradiated the surface of the soil, some uh, some part of the soil will going to be heated due to the solar energy. Now, what does it mean by heat transfer here is that how well those heat energy, will going to transpire through. Uh, Now, the uh, the desirable so the so-called desirable properties in terms of heat transfer is that it will going to uh, a good soil structure will going to have a good heat transfer, I would say. Now, in this case, I would say all soils were going to have the ability to transfer heat, except for those that have enough air inside. Now, in this case, for those soil that have a lot of air and also moisture inside, we're going to have the ability to sustain sudden increase of temperature. So when the soil is irradiated with soil, you might going to think that, oh, the temperature will going to increase very significantly, and due to that, not many life form will going to exist in the soil. Now the answer is yes or no. The answer is yes or no. Now, it is not going to happen if the soil have a lot of air and water inside, which is the characteristic of a good soil properties. Now, why do I say that? Is because when you have air, those air will be the so-called what we call penebat, yeah, and they will have the ability to stop the heat from transpire through too much. And another thing is that if the soil also contains moisture, it will be able to absorb the heat and yeah, sustain life. Because if the temperature exceeds 37 degrees Celsius, that is the temperature where all the proteins are going to get denatured. And if you learn biology, in any life forms, they depend on healthy enzyme to function. So if the temperature raises too much due to high heat transfer, then the soil might get too hot, and those organisms, including plants, okay, any organism, plant included, might going to be affected lah. Yeah. Now, another thing is about aeration. Now, last time when I explained the introduction about soil, I remember I told you that the soil needs air. And why is that so? Because during nighttime, the plants will need oxygen for respiration. So don't think that the plants will always going to do photosynthesis. Okay? Now, photosynthesis will going to happen only during daytime where there's sunlight. Then they absorb carbon dioxide using their leaf. However, come night time, there is no sunlight, and then they're going to conduct photosynthesis just like human, but using their roots. So if the root is doing all the job, then the soil must have enough air inside, and hence a good soil structure is needed to allow respiration of plants to happen. And then not only that, porosity also allows the movement of nutrients and also moisture into the soil. And as you know just now, high porosity means flowing means the material, including air and also water, can flow through freely. Yeah, but of course lah, if the porosity gets too high, then maybe it's not going to be too good for the soil to sustain nutrient. So not too high, not too low, so to allow air and water to be flowing through and retained inside the soil. So these are the structures that the textures that you're going to be able to see based on different soil texture. Now, some of the textures might be very small due to high content of clay, but because of the nature and also the weathering patterns, they might going to give you different uh, texture, structure. So as you can see, the first one at the top left, single grain. Now they look more or less like sand grain, but it's not necessarily due to high percentage of sand. Sometimes any soil that have high clay content might going to give you this structure as well. Now I'm talking about those organic soil. Okay, organic soil might going to have like single grain with a very small grain size. So they might aggregate, or organic soil might aggregate to form small soil aggregate particles that looks like sand grain, but not exactly that. Now, this also could be due to the high percentage of sand or gravel. So they could be very small, but these are the size lah, yeah. And then get well, if those aggregates gets bigger, then they might going to form granules. So these are the so-called small aggregates. In Barcelona you call it ketulan, small ketulan tanah, or the small particles. Then these are due to aggregation as well. Now if it's not aggregation, gravels also might give you the same thing. Yeah. Now, the interesting part is in the middle and also the right hand side. Now, blocky soil are due to the lack of weathering. So when you can see block of prismatic soil, usually these are the ones that exist in arid countries. Arid means the areas with the lack of water. Now, when you don't have enough water, I mean there won't be too much of weathering process, and this is the result. If there's lack of water weathering process, soil particles do not break up too much and they tend to stick together. So blocky is one thing, the other one is prismatic lah. Now if you look at prismatic, they are like a small extent of water flowing through that causes all this columnic structure, prismatic. Yeah, so you can see a lot long column that extend deep into the soil. Those are also due to lack of water weathering. Now on the right hand side also is platy structure plus massive. Massive is like the whole block of soil. So you can imagine these are due to the lack of weathering as well. The least I would say, but the way how platy soil texture is being formed is due to extensive deposition and drying process. So each of these plate that you can see right here can be separated, and they were formed due to continuous and repeated cycles of wetting and drying. So why does all these plate exist one another? It exists due to the deposition of clay or sediment. Now these sediments might not be limited to the small particles of clay, but it also could be involving larger particles like silt. So they will deposit on top of each other. Now once those are conducted, once the deposition has happened, the next cycle will be the drying process. So after wet season, where the deposition of soil particles on top of the layer, the following dry season we're going to compact it. Dry it, compact it, may involve some chemical process So the chemical process, we're going to cement and solidify this so-called soil sediment, and hence you have all this platy structure, one piece after another. Yeah. So if you look at this texture, they were affected due to the different percentages of soil, like sand, silt, and clay. They are also affected due to the content of organic matter, and finally the weathering pattern. So weathering pattern plays a lot of role on this texture. Now I'm not going to read you all those shapes in this soil structure, but I believe you can like read it yourself. There are actually quite a lot for you to like read through, so take your time, read through it. How does a spheroidal soil compare to a granular soil? So yeah, you can say that it's kind of hard to learn this one because you need to like feel or see something, isn't it? So don't worry, take your time, read it. If I say spheroidal from the word itself, sphera means round shape. So any shape or structure that is called spheroidal, you can imagine that those are the round shape. Okay, the soil texture, uh, the soil structure looks very round, does not have too much of angle, and they can be big and small depending on how big is the aggregation. So if it's round shape, it could be consists of two types: granular or crumb. Now crumb soil is the good one, I would say. It is very porous. That means it will allow air and fluids to flow through, but yet usually this kind of soil will be able to retain moisture, minus the sand. Sand do not crumble. Sand actually crumbles too easily to be part of this here. So we're talking about usually the loamy soil, okay, the loamy soil with a balanced composition of sand, silt, and clay, plus soil that have high organic matter. So usually those are the one that will be very crumbly. Crumbly means you can hold a large aggregate, a large piece, a large soil aggregate, and when you lightly press it, it will going to crumble and falls apart. Okay, so you can imagine soil, you press it lightly, it will crumble, it will break apart. So these are what we call crumbly. Sometimes we also call it friable soil. Also the same definition, same description. Yeah. So those are the good ones, yeah? Good soil structure. And like you can see right here, granular, round, not exactly round, but close, very close to round shape. And most of the good soils, they are looking like this, yeah. And as you can see right there, they are commonly found in A horizon. Why is that? If you still remember, A horizon is the second horizon from top. Definitely is organic, the O horizon that has a lot of organic matter. And A horizon is the layer of soil that have mineral phase and possibly the second highest organic content the due to the weathering process and also what they receive from top from the O horizon. Now, due to the high organic content, they tend to stick the soil the soil particles like clay and silt together, and that is why they form granules, larger granules of soil, which are crumbly because they don't stick permanently. They only stick because of the high organic content, and when you press it, they crumble. And granular soil also may also exist in the B horizon because this horizon may accumulate larger quantity of clay particles, and because of that, they also aggregate. Now, this time, when it is in a B horizon, due to the high clay content, they aggregate due to the clay particles, higher percentage of clay. Clay also can stick together and they aggregate. Yeah. with different moisture content. But of course, this is the one that I said that is good for the soil, the A horizon. They they aggregate together due to high organic content. Okay, the next one is plate-like platy structure. Now these are the structure that where we see earlier. Plate-like, they have like a lot of like layers after layers of uh, soil soil texture. Um, and here they say it is common in the E horizon. So let's do some recap again. It start with O, then A, followed by B horizon, OAE, BCR. So E horizon sits between A and B horizon. Okay, now the E horizon sits between A and B horizon. Now earlier I told you that the B horizon might accumulate clay. The E horizons here might also have some sort of clay to give you the plate-like platy soil texture. So let's see. It is made of soil particles aggregated in thin plates and sheets piled horizontally on each other. They overlap and it's greatly impairing water circulation. So, like I told you earlier, they were formed due to high percentage of clay. Okay, they are formed due to high percentage of clay, in which the wetting and drying process causes all these layers. And although earlier slide says that it is possibly found in E horizon, but I would say due to the weathering cycle of wetting and drying, I would say usually this is found in the A horizon, the top one, because the wetting and drying process, in order to have all these cycles, usually the outermost surface of the soil, we're going to have this ability to be exposed to the wetting and drying cycle in order to form this platy texture, a platy structure. So I would say A horizon lah. A horizon plus the soil have a bit more clay particles in order to form this. Well, of course, uh, with this texture, over a long period of time, with pressure and also heat, they might going to like continue and proceed into the formation of sedimentary rock, because sedimentary rocks looks like more or less like this. Only sedimentary rocks is cemented, so they will have layers, but they are harder than this one. Yeah, this one is still soft. Yeah, the platy soil structure. Okay, block-like. So earlier I told you block-like structure, they are large pieces due to the lack of water movement or weathering. So where can you find this blocky structure? It needs a fair bit of clay in order to form all these aggregated blocks. So as you can see right there, the B horizon. It may also occur in the A horizon, but the key is it must have enough clay and not much of aggregation lah, or at least the aggregation happens only on the mineral phase. And most likely the block-like structure will going to involve very little organic content, while the granular texture involving a lot of organic matter, the block-like or the blocky soil texture involving primarily clay. So this is an example of the subangular blocky structure in the B horizon. Doesn't look too blocky to me, because I mean the lines between all these blocks are not too apparent. Yeah. But if we convert it into the image, a diagram, so you can see this what we can see in terms of the blocky or what we call subangular blocky structure. And like I said to you, it involves primarily clay mineral particles and they aggregate. And if that is so, usually they will aggregate in larger pieces. And when they get too large, they don't count as uh, the spherical texture or the or the one that we saw earlier, the spherical texture, but rather we give them another texture, like we call it block, which is larger than the spherical texture. Some other ones include prism-like. Now, prism-like also found in B horizon, and they are columnar in terms of the texture. Now, this one will be found in the arid regions due to the lack of vertical water movement that causes all those breaking up and also the transfer of soil mineral downwards. And when you talk about prismatic, so they can be seen like this soil looks like they consist of a large vertical column that are like uh, I mean placed very closely one after another. Now, why they form all these long columns is that these so-called gaps between the column are formed due to water movement. Okay, and because of the lack of water movement or the lack of water weathering, or maybe due to the poor drainage, the soil particles will be intact and they are going to be selectively I mean the weathering process happens selectively, and due to that selective and the water weathering, these giant columns of soil is allowed to form. So once they form, this is what they look like. Yeah, they're quite big, they're quite long, and they're standing vertically. Now, when I say long, doesn't mean that it extends all the way to the deepest horizon. No, I did not mean that. What I mean is the entire horizon. Possibly it extends possibly maybe into one horizon only, and this horizon is the B horizon. And from my experience, the B horizon usually do not extend more than 2 meters. It could be slightly more than that, but it's around 2 meters. Probably 1 person height. It's not very long, I would say. Yeah. So this is how it looks like, prismatic structure in the B horizon. And in order to get to B horizon, you need to dig. So once you dig deep enough, then the layering bukit lah. Usually, sometimes you can see things right here. Yeah. Okay, I think there are still some more to cover. So these are the description lah. Yeah. Um, in terms of the structure that we can use, the terms or the words that people use in defining the soil structure is the shape of the piece, like what we have go through just now: angular, subangular, prismatic, plate-like. These are the terms that people use first, and then once that is given, then the size. How small is are those particles? Are they fine, medium, or are they coarse? So if it's fine, that means the clay is there. If it's coarse, that means more sand is there. So the definition, I mean the description given to soil structure, kind of like closely associated with texture as well. Because in terms of texture, you also need to define, are they smooth or are they coarse, which indicates the presence of clay and sand respectively. Okay? And the other thing is the grades. How strong are those structure? Are they strong or are they weak? Now, in terms of strong or weak, I would say how well they can sustain those structure. If they press hard, then are they still being able to sustain those structure? So those are the words that people use in order to define or describe soil structure. So you can see the examples right there, yeah. And this kind of structure, usually they are not too They are not too frequently used lah. Um, unless you're geologist. If you're geologist, then probably you're going to use a lot more of it. But if you are an agriculturist or botanist, um, we just use whether they are friable or not, or are they having large aggregates. So geologists lah, usually you're going to see all this that description. When we talk about density, there are two types of soil density that we're going to talk about. One is particle density, the other one is bulk density. Okay, I'm going to start with the particle density first. Okay, now because this is quite straightforward, uh, in which this will going to be exactly what you learned before this under physics lah. If you still remember, for density, to define density is just merely weight of a material divide by volume, and this is exactly that. So if you can find the weight of a soil, you can just straight away divide its volume, and then you have it, the particle density. Okay. And then the unit, possibly it could be in grams per cubic centimeter or kilogram in cubic meter. But let's not forget volumes. Volume most of the time is measured by like liters or milliliters. So those are the units also you might going to encounter like, yeah? Kilograms per liter, or maybe grams per ml as well. So this is how we calculated the mass of oven dried solid soil. So remember, for calculating for determining particle density, the soil after being collected will usually be first air dried. Air dried means you just put it in one corner, you use the room temperature and let it dry first, but it's not completely dry because there's still some trapped moisture inside the soil. And in order to completely remove every single moisture in the soil, you put it in oven. What's the temperature? It could be 80, it could be 60, but as long as it's dry with constant weight, then it will do. Not necessarily 100 degrees Celsius lah. So once that is dry, then only you can use those soil to determine particle density. Yeah, and so divide by volume of soil, and there you have it. Particle density of between 2.6. No, it's not just 2.6 because why? It depends on how dense is the soil, because some soil may be denser due to higher percentage of rocks. If you have more like mineral phase like sand inside there, then the particle density might be a bit higher because they are more dense. If they're less dense, then maybe they are lighter. So some of the soil may have lighter component like organic matter. If there are organic matter inside, it is not as dense as the mineral component, and hence they might have a lower particle density. So I will going to move on to the next one, next slide. So these are the examples like, yeah, if you're comparing the density between different materials, different minerals, you can see as water having 1 gram per ml density. So those are standard like, yeah. And when water have a lot of like dissolved components inside, this density also will increase accordingly. Why? Because apart from water itself, they are also carrying the minerals, which ultimately is still heavier than water. So that's why lah. Naturally, water will not having like density of 1 gram per ml, even with rainwater, because sometimes rainwater also is heavier due to the particles that it incorporated in rainwater. However, if you look at the others like quartz, feldspar, mica, and clay minerals, they are like quite consistent, sitting between 2.5 to 3.0. It's not going to be more than that lah, because minerals they are like quite constant. It's not like those minerals were going to get denser than that. Well, it could. Some minerals can get even denser than this one. Like for example, the metamorphic rock. Last time we learned about metamorphic rock. Those can get even denser, because if you still remember, metamorphic rock are formed due to high pressure and also high temperature. So due to the high pressure, some of the minerals can get denser. Yeah. Okay, so enough with particle density. Now the next type, the second one, bulk density. You might be asking, what is the difference? Now, here is a major difference. For bulk density, apart from the different symbol here, they differs due to the fact that in the definition. So in bulk density definition, they are going to consider the air that are trapped in the soil as well in the calculation. And most of the time, naturally speaking lah, the soil that you can find outdoor naturally, they will not going to be that compact, and they're going to incorporate a bit of air inside, as with the good, I mean the soil with good structure, they will have air inside. And in the calculation, they were going to calculate the formula is still the same, weight over volume. However, in the soil sample that is used to calculate bulk density, we were going to try our best to retain the porous structure of the soil during the soil collection. And with that, logically speaking, the weight would be much lesser than those that you're using that you're using for determining the particle density. Because if you still remember, in the particle density, the soil must be oven dried. So when I say oven dried, those are the one without moisture. But during drying process in the oven, when the moisture is being when the moisture is being removed, usually it will going to have a little bit of capillary force, in which during drying process it will going to pull the particles together and sticks them together. So technically, the air will be removed as well when the moisture is being removed. As the moisture evaporates, the air in the soil will going to be decreased because they are shrinking during drying. Yeah? However, in the determination of bulk density, no drying is required. No drying. During this experiment, students will just need a cylinder that is made of a sturdy iron. So during the determination of bulk density, they will hammer this cylinder downward into the soil. So the middle of this cylinder, no pressure will be exerted. They were going to knock the side of the cylinder downwards, and then after that collect the entire cylinder with the soil inside in the inner part of the cylinder, and they're going to carry it. Then after that, they determine the weight and also the volume. Okay, so that is the main difference. And logically speaking if the air is included, is considered during bulk density calculation, most likely it will going to have a lower value. So bulk density usually is lower than particle density. Because why? They consider air, so that's why they are lighter. When they're lighter, lower bulk density. And as you can see right here, there are some tendency or some trends inside here that can be observed, in which if a soil consists of majority mineral parts, mineral components like sand, silt, and clay, if they have more sand, silt, and clay, they tends to be sitting between 1.0 or 1.8. But I can tell you it's not just 1.8. Sometimes it can get even higher than that, 2 or 3, because sometimes the soil might not even have air inside. So that is the highest they can go. Can they go higher than 3? Logically speaking, no. Because if you look back at the particle density earlier, right here, the highest possible particle density is only 3. It's not logic to go higher than 3 usually, yeah. But it could, sometimes, Some soil they are more dense. We don't know. So those are the mineral soil. Okay, and when we use when we have a soil sample with relatively higher organic matter, they tend to get lighter, not just because they have more lighter organic material inside, but the fact that organic material also cause aggregation. Aggregation means they cause the soil particles to stick together to form ketulan, or in English we call it aggregates. So when aggregates is formed, the space between two different aggregates tends to be expanding, and this is where you have more air in the organic soil. So lighter due to the fact that organic matter is lighter, but also due to the increasing air pockets from the aggregates. Yeah. And because of that, with more air inside the organic soil, they tends to get even lower in bulk density. It is less than what I would say. Yeah, this is accurate lah. 0.1, I probably haven't seen so much of that, but 0.5 or 0.6 lah. These are the normal range for a soil that have a healthy amount of organic matter. I think probably 0.1 are those soils with more than 30 or more than 50% of organic matter. Then only, yeah, it's 0.1. Could be peat lah, I would say. Okay, so bulk density, the trend. Why this is so important? It is important because only with bulk density you can predict the nature or whether the soil is good for agriculture. Now, by relying on bulk density probably is not really an accurate estimation of how good is one soil, but it is enough for farmers to kind of guess. If a soil is having a low bulk density, that means they have enough air, and that tells us that the aeration should be there, the infiltration should be there because of air inside the soil. So these two factors are very, very important to allow healthy germination from the seeds. Because when a seed is germinated, the root will need to expand. Imagine lah, the germination happens on top of a rock. There's no room for them to even expand the root network. And how big a plant can grow, it depends on how wide the root area can expand. The bigger the root can expand, the larger or the healthier the plants can be. Because the root is where they absorb moisture, absorb nutrients, and do respiration. So an aerated soil is required lah for a healthy plant growth. Okay. And also, not only the farmers is preferring soil with low bulk density, local government, I would say, or you yourself will probably want to have a, a porous soil, because with porous soil they can absorb moisture, retain it, sustain life, and most importantly, avoid flooding. Now you can see nowadays YKL area, the developed areas, they have constant flash flood because that also contributes due to climate change. Sudden change of climate, unpredictable. Suddenly there's a huge rainfall coming in, and then developed areas like KL caught off guard. Do you know why? Because most of this developed area, the surface of the soil is covered by structure like cement or asphalt, your jalan berturap. These are the surface that do not allow absorption of water, and yeah, flooding happens. So having a low bulk density will help avoid flash flood. Okay, now the bulk density may be affected due to compaction. Now this compaction may happen artificially or naturally, but one thing that I need to remind you here is that soil bulk density can be said a compulsory field trip experiment. During field trip, you must do it because it's so easy to do, and it's so meaningful to know the bulk density. However, in order to do this experiment, I think I informed you just now how it's done. A cylinder, you hammer it down, but during the hammering process, you have to make sure you hammer the side of the cylinder, not the middle of the cylinder. Because if the middle of the cylinder is being hammered, then compaction happens, and that's it. You have to repeat again. Those are the soils that are compacted and do not accurately reflect the pores or the structure of the porous soil. Yeah? So you have to repeat again. Now, I think I've explained to you earlier why this is so good for agricultural activities, because the air is needed inside for healthy growth. Now, if a soil do not have a good bulk density, traditionally tillage is required. Now, tillage in this sense, in Bahasa Melayu, we call it membajak. Membaja means you have a kerbau, and then you have somebody with the tools inside, and then you bulldoze the soil column so that you break them apart. So soil are hard. They break, I mean, farmers previously breaks this soil, tile the soil to make it softer and allow healthy germination of the plant seed. However, tillage is said to be harmful to healthy growth of the soil, because in tillage also you also destroy also the organic matter. So bulk density lah can tell you whether a soil needs a tillage or not, because if you can, you avoid manual tillage as much as possible. Now I will explain later lah in the next subject when we talk about soil organic matter. um, because tillage can happen naturally, and those are the ones that we prefer. Okay, next one, bulk density, why they're so important. I have already explained to you exactly all these things, so I will just skip lah here. Compaction also is something that is related to what I've said earlier. I think I want to elaborate further lah compaction. Now, just not because I told you the compaction factor during determination of soil bulk density. However, I'm going to cover lah the impact, the actual compaction that happens outside, and also its impact. Now, usually compaction happens. Now, these terms lah here, what they mean by compaction is artificial compaction. That means it's caused by human activity. Now, it's not that human purposely want to compact the soil, although it is, because civil engineers lah. If you ask any civil engineers how they would like to have their foundation on the soil to be, they would usually going to tell you they're going to have like a steamroller. Do you know what is steamroller? When you have like a road process where you want to turap jalan, then you have like a huge vehicle with a big steamroller in front. Those are what we call steamroller. Um, Construction lah usually will have that one, especially when we talk about high-rise building. Because why? You need a very stable soil surface in order to have a high load-bearing capacity. Otherwise, today you build the house, tomorrow it will going to fall down. Kan? So compaction is what the civil engineers like to do lah. However, the impact. Okay, let's talk about impact. Now, if the soil is being compacted, can we still plant something on top of it? The answer is yes or no. Yes, small plants, no, big plants. Because if they are compacted already, then possibly the plants that will have a large root network will not going to grow too big and possibly not even survive. Okay, that's one. Number two, if it's too compacted, water cannot flow through, then what? Flash flood. And hence, developed areas with high soil compaction usually will have to resort to having a very effective drainage system. You must have a big longkang. So if you go to big cities lah, like Shah Alam, like Subang, these are the town area that are like well developed, and every major road, you look at the side of the major road, they will have a large longkang, the drainage. Because why? Most of the soils that are located in developed areas, they're so compacted that naturally it cannot absorb too much of moisture. It still can, but very limited. And with large, with a high rainfall, flash will happen. So that's why. Yeah. So compaction, is it good or not? Um, it's a little bit of both lah. If you want to build structure, compaction is mandatory. It's needed. However, if you're into nature, if you're into agriculture, it's quite bad lah, yeah, for plant growth. So to measure compaction, you also can be having this small instrument in which the needles or the pole, the narrow pole at the bottom, can measure force. So if you press it down, if the soil is too compacted, it will going to exert larger, it will going to require larger amount of force for you to poke through the compacted soil, and it will be reflected by the meter. I would say this one sometimes the MADI officers might going to use it to measure compaction. Unfortunately our faculty do not have this one. Although this instrument is not really that expensive. Yeah, it's not that expensive. Okay, now moving on, the next part that we're going to talk about is soil porosity. Now, earlier I told you porosity is how much of air inside and how much of water can flow through. I would say the more accurate definition for porosity is how much of air, how much of total volume of air. Now, as you can see right here, the formula for porosity says volume of pore space divided by total soil volume. So how much of air? Total air. They haven't say what are those pores? Are they small? Are they big? Now, for your information, they have large and small pores. And porosity will not tell you that. They only tell you how much of air inside a soil column. So what does that mean? That means a good soil usually will have high porosity, usually lah. And porosity can be measured in two ways. You measure by placing an oven-dried soil, and then you divide by the volume of soil from the cylinders of the soil column that you have determined. Beyond that, I think you can also use, you determine the amount of water. Or there's another way. The other way is that, okay, let me finish this slide first, okay? Now, the first way is you dry the soil and you determine the space based on the weight loss of the drying process. Now, for the weight that is lost is due to disappearance of water. Now, water, as you remember earlier, what was the density? 1 gram per ml. So for every 1 gram of weight loss, that indicates 1 gram of water is disappeared. And if 1 gram of water disappeared, that means 1 ml of water also was there in the soil. So from the drying process, you can estimate. Due to the loss of water, you can also estimate the volume, okay, or the air, the porosity of the soil. Okay, now this is another way where you can determine the porosity as well. From total volume of soil divided by the volume of air, although to directly measure the volume of air may require specific instrument. Now you may not know that there's one instrument called surface area analyzer, in which they pump nitrogen gas into the soil, and then after that they're going to count how much of nitrogen gas is being released back, and from there they can know what is the porosity. But um, I think there is a simple technique, lab techniques, very simple to do this, in which a soil, once collected from the site, the soil column still intact, the soil inside, they were going to flood the entire column with water. So they're going to flood it on top of the surface. So once the flooding is completed, then they'll start the drying process. So from the weight loss difference, they will be able to determine the volume. Okay, the volume that's in the soil column, and after that the porosity lah, yeah. So either direct measurement from flooding and drying process, or the other way is by using instrument for direct measurement. So these two are direct measurement, I would say. There is another way, which is even better, I would say, indirect determination. This one, yeah. Now, in order to determine porosity, first you need two parameters, the bulk density and the particle density. So if you use this formula to calculate, you indirectly can determine the porosity as well. Because if you still remember, particle density is the density that excludes air, whereas bulk density, they include air. So if you put them into ratio, you basically can determine how much of air based on these two parameters, and you calculate it. It's quite accurate, I would say. It's quite accurate. And best part is, it's quite straightforward. No need to do so much of work. So you can imagine, yeah, after you have determined bulk density, then you can straight away determine the porosity as well. Now, although porosity is not something that farmers usually do, usually they'll just be happy with the bulk density, but porosity is important for scientists just to gauge how much of air that a soil column has, and based on this porosity, it also can tells you how much of water that they can absorb. So usually it's climatologists would like to know this, or meteorologists who want to see, or town planners, they want to see how much of air inside the soil and how much of water they can sustain before it starts flooding. So porosity is important in that sense. So then again, the formula and then the porosity. Now these are the range that we're talking about. For soil that have low porosity, the range is 25, but I would say it's much lower than that. And don't be surprised, sometimes the soil can have a very high porosity, up to 60%. Now, if you want to know the highest possible porosity, I would say is peat soil. Peat soil is close to 100% of the soil is organic. Some may reach until 90% organic matter. Uh, wait, correction. It's not 90%, not 90% organic matter. It's 30 to 50% organic matter. So if you have peat soil with that much of organic matter, they will tend to absorb a lot of water. So how much of water they can absorb? 90% in weight basis, which means that if it translate into porosity, it's also close to 90% porosity. So it can get that high. Okay, and usually it happens for soil that consists of large amount of organic matter, and because of that they absorb a lot of water, and due to those presence of water, that is where the porosity comes in. So a bit of examples that you can see here: loam, silt loam, and clay. No peat soil. If it's peat soil, it's much higher than that. So even with loam here, it's already like 60 to close to 60, 63% of porosity. Okay, so moving on, when we talk about porosity, no pores are created the same. Some are bigger, some are smaller. If it's big, it's called macropore. If it's small, it's called micropore. If it sits in the middle of these two, it's called mesopore, in the middle. And they have a different size, different particle, different diameter in terms of this pore size. Now, now these are the three names that you should put in your head: macropore, mesopore, and micropore. Because based on these three different pores, the ability of water to be retained in the soil varies significantly. If you have a lot of macropore, water flows through, like sand. If you have a lot of micropore, water traps inside there and does not flow through that much. Which one is better? Of course, the action inside micropore. We want moisture in the soil because that will sustain life, but not too much, of course. Um, then what size can do that? So these are the pore size that differentiate micropore and macropore. Okay, here's what you need to do. You need to know the words, and you also need to know what are the pore size that is associated to these three types of pores. Okay, I won't go to read you the size, but you need to know. Micropore, what size? Macropore, what is the size? Okay, whatever you talk about here, they are sitting in the micron region, yeah. By the way, if you look carefully, there is one correction that is required, which is macropore. Macropore is not 7.5, it's 75. So later on, maybe you can do some correction later lah. And with that, I think I also want to do it immediately right here. So this is correct. If you have your slide, correct it yourself, yeah? Okay. Moving on, we're going to describe what is macropore, mesopore, and micropore. So when you have macropore, they are large enough to allow movement of water freely and through, sometimes too fast. So sandy soils lah, you can imagine that. They flow through too fast and they cannot retain those moisture. Good or bad? Of course bad lah. Because like I said, we need water to sustain life. However, they don't have problem trying to accommodate these things. When the root is expanding, no problem. However, there's only one problem. If it's too big, moisture cannot be retained. Ultimately, it's not too good as well. Yeah. Okay, what about mesopore? Now, mesopore is slightly smaller. Now, usually, if it is smaller, it can retain slight amount of more water. Because when the pore gets smaller, there is a force we call capillary force. Okay, if the capillary force is there, then the moisture can stick to the walls of this mesopore because they're small enough. Yeah, and usually this moisture, if they stick around, they are said to be the field capacity moisture content. You see, different soil we're going to have different amount of water based on the pores that they have. So for the moisture that can be retained due to mesopore, they are said to be consisting like field capacity moisture. It's kind of hard to explain to you what is field capacity, but what they say is like after several days of putting it aside, like I told you, the soil still have moisture. Those moisture, they are considered as field capacity. Okay, so next one is micropore. Now this one is the moisture that can only be removed after oven drying. So after you oven dry it, all the remaining waters still trapped inside the soil will be disappeared, and these are what they call the micropore. Now, if the water is removed after oven drying, usually these water are trapped deep inside the micropore and they don't move too freely lah, yeah. So micropore, they're not so good in terms of the availability of water because what? If the water is trapped inside micropore, the root is not small enough to go inside and absorb it. However, because this moisture are trapped and virtually no roots can go there and tap it, it will help sustain microbial activity because micro also needs moisture, and because they're so small, microbes can go in and use it. And usually this micropore also is the so-called the medium or the platform where all the microbial activity will going to be sustained inside there. So is it good or bad? Yeah, a little bit of bad, but primarily also good because it sustains microbial activity. That's number one. Number two is that this micropore also is very important in terms of environmental cleanup. If you have pollution happen in the environment, you can use any mineral with a lot of micropore to do all the absorbing. Like for example, if you have pollution in the soil, usually we're going to mix a little bit of clay. Some clay can absorb, and because why? This clay, they are so small, they have a lot of micropore. So the soil component that do all this cleaning up usually is clay. And why? Because clay have a lot of micropore. Micropore allows absorption of contaminants inside there. Okay, students, let's restart our lecture back again on porosity. So earlier we determined how to calculate the soil porosity and also its impact, micropore, mesopore, and micropore. So let's move on lah, yeah. factors that affect the porosity and bulk density. Now, what's not, apart from compaction which is artificial, the next three factors we're going to discuss is due to natural factors. Okay. Now, first one being soil texture. Let me see if there's a slide there. Yeah. So the first one is soil texture. The next one is organic matter and also soil depth. I think I've kind of like in the explanation earlier, I have already covered how texture and organic matter cause the porosity. So I won't going to go back into that one. Possibly I'm going to explain according to soil depth lah, yeah. So later on, let's see the slides. So as you can see right here, sandy soil tend to be less porous than silty and clayey soil. Now in this case, you're probably going to like wonder why sandy soil is less porous than clay, in which when we talk about water flow, sandy soil is the one that can have a lot of water flow through, but not clay. But how come clay is more porous? And if you remember earlier, how we determine soil porosity is that we will dry every single moisture from the soil in order to determine the entire porosity. And because of that, clay would have the highest porosity simply because clay will have high water content, and they have this water content to have this aggregation with another clay particles. And because of the high volume of the micropore, and also the moisture that they can entrap, that is why they have a lot of porosity. And not only that, you can say also porosity is having the same trend with surface area. Clay also have high surface area. Apart from porosity, they are like same trend. Yeah. Of course lah, it cannot be said to be like the bulk density, because bulk density depends on how much of organic matter inside. So if you look at all these three, whether it's sand, loam, and clay, they are more or less the same lah. More than one. Yeah, more than one in terms of bulk density. Okay, now texture, I think I've explained to you earlier the texture. If they are aggregated, they have more air between aggregates, and that's why they have higher porosity. I would like to go into the next part, which is soil depth. Okay, now in terms of soil depth, the area that is said to have the most porosity usually sits on top of the horizon. The deeper horizon will have less porosity for obvious reason, because when you are at the bottom, the bottommost of the soil horizon, you have to remember that that can be as deep as several meters. And when we talk about several meters, soil is very heavy. Mind you, soil is very heavy. Having several meters length of the soil on top of the most bottom soil, meaning that there is immense amount of weight sitting on top of it, and because of the high pressure and the high weight, the enormous weight sitting on top, they will tend to have compaction. Okay, now this compaction happens naturally at deeper regions of the soil. So deeper regions will tend to have less porosity because they're already compacted. However, if you remember on top, what's on top? O horizon plus a lot of living life forms on the O and possibly A horizon. And because of the contribution of organic matter, and also with the help of soil organism. Now this soil organism, they not only living inside there, they also move inside there, like earthworms, insects, ants. They live inside the soil and they make their own place. And because of that, they also create a lot of macropore, the spaces in the soil. So on the horizons nearer to the surface, usually they're going to have higher porosity. Okay? It's easy as that. Okay, now permeability is another physical factors that also quite important, um, and they are not exactly the same with porosity. Earlier, when we say porosity is how much of air inside the soil, permeability in terms of definition is how easy air, water can move through the soil. So earlier when I told you sand will have porosity lower than clay. However, the permeability for sand is higher than clay, as what we all know. Because why? They have a lot of big gaps, big macropore to allow water to flow through. Now, although this macropore may not translate into high porosity, but they definitely translate into high permeability. So remember, yeah, high permeability is usually associated with soil with high amount of macropore. You have a lot of macropore, big pores, they can flow down. But if the soil have a lot of micropore, the permeability will be very low. Examples such as clay. Clay have high porosity, but they have high porosity due to a lot of micropore. And for your information, I told you just now, micropore, they trap water. So when they trap water, there's no more air that can connect outside and inside, so they cannot flow through. And therefore, the permeability for clay is much lower than the sand. I think enough said. Now, permeability, why is this so important? You cannot get too high permeability or too low. It has to be a balance because you must allow water to flow in. And once they flow into the soil, they should be retained a fair bit inside the soil. So having a macropore will not do this. Having too much of micropore also is also equally bad. So it must be a balance layer between. They allow water to flow through and they must be retained. Now, for the next part, we will talk about soil color. Now, this one is completely different because earlier we talked about bulk density, particle density, porosity, permeability, whatnot. Those are the ones that are involving regarding the physical properties in terms of air versus, in terms of air and also solid. But this one is a bit different. We look at the color. Now, why do we even need to look at the color? Because why? When we talk about color, is usually associated with appearance. Whether or not it is a good idea, well, maybe it is because some people likes to have their soil more fairer because fair probably looks more attractive. But in the in agriculture and also in environment. Being fair, the soil color, being fair means not good. Usually not good. Because for obvious reason, guys. Earlier I told you a lot of benefits for having high organic matter. And if you still remember, organic looks ugly. Not to say ugly lah. To me, it's good. I like dark color. But if you hate dark color, then possibly it's not your favorite color lah. So a good soil will have a dark color, but the being dark is just one indication. When I use the word indication means that I'm not certain whether it has high organic matter, but usually it is. Yeah, usually that is the case. If a soil is dark, usually it means high organic matter. But what about if the soil is red? As what you can see outside, right? You you buka one area and you bulldoze the entire soil column, you get red colored soil. What does that mean? That means a lot of things, kan? Okay. Now, more surprising is sometimes when you go to some areas and you want to look at the soil color, they might even appear as gray, white, bluish, greenish. Yeah, these are the colors that you can see from the soil. So what do they mean? That means they have different content of moisture or different content of metals inside. Although here in this slide you can see iron oxide, but iron is not the only metals in the soil. It could be others, but it's quite safe to say that you're going to see more iron than other elements here. And of course, organic matter, which is dark, as I said earlier. So soil color is affected by organic matter, the wetness or the moisture content, and also the aeration. Because in this case, Aeration also dictates how an iron looks like. Okay, iron and manganese. Based on different oxidation state, they look differently. Okay, before I continue lah, if you learn chemistry before, there is iron 2, Fe2 plus, and also Fe3 plus. Fe2 plus is green in color, okay? Whereas Fe3 plus, the one that you usually see, is red in color. So that's why the red soil that you see outside, they are most likely consisting a lot of Fe3 plus. So that's why they look red in color. If it's more intense, it looks like karat lah, dark, but actually it's reddish brown. Okay, reddish brown color. Okay, so as you can see right here, color is useful to estimate what are the usual or possible content in the soil, but the one that people usually refer is dark. The word dark. How dark? Is it dark or is it not dark? If it's dark, then it's probably good, because usually dark color associated with high organic matter, and that is good because you definitely can tell if it's having high organic matter, then the porosity should be enough, the bulk density should be low enough, and a lot of good things that follows. Yeah. Now there are other colors that you can find here, which is dark brown to black, white to light gray, red, bluish gray, mottled red. So yeah, dark color because associated with organic matter. What I'm trying to show you is what happens if you have gray color. Okay, now gray color is dark plus white. Well, probably a bit more white, because here um, if the if the soil is lacking of iron, usually it will look white, just like sand. Sand, what is the color? White color, isn't it? How often do they get gray? Well, not so often, unless it is mixed with dark component, then it gets a little bit gray. But if it's totally white, that means not much of impurities inside. It's purely mineral. What kind of mineral? Maybe sand, maybe silt. But even silt as well, you are going to see some reddish color. Yeah. So it depends lah how much is the composition. Limestone also, lime here means limestone, also appears as white, like batu kapur, white colored. Gypsum also is white colored. If a mineral appears to be white, most likely those mineral consists of alkaline or earth alkaline metals, like calcium, magnesium, sodium, or maybe potassium. These kind of metals usually don't show color and they appear as white. So if you have sand or maybe majority of this metal, they appear as white. There's only one way that you can see other than white color, which if you have transition element. And earlier I showed you iron. Iron is one transition element, which they show you red or green color. Now, if they're oxidized, then it's usually red, just like iron. Oxidized to Fe3 plus is red. However, in some conditions where the soil do not have enough oxygen, mostly moisture, but low oxygen, iron can turn into iron 2 plus. Iron 2 plus, as we know earlier, is green. However, due to the complex mixture of other components, it might appear as blue, bluish green or bluish gray. Yeah? Just like this one right here, yeah. So usually you will see bluish color from clay. Clay, why I say clay? Because earlier clay will be able to sustain a lot of moisture, and because of high moisture, usually oxygen cannot go in. So if a soil contains iron inside, they will be reduced into iron 2 plus, and because of that, it looks greenish, or in this case a little bit bluish, because it makes a little bit of other whitish color. It looks blue, but actually it is due to the Fe2 plus, which is green color. Yeah. Okay, mottled color, well, these are due to the oxidation and reduction process of iron. So yeah, if it is waterlogged, then it's a reduction. You get a little bit of green. If it's oxidized, then there's a little bit of red. Now, how do we quantify soil color? Now, there is a booklet we call Munsell color chart. So here you see lah, of course, why is named Munsell? Because that guy named Munsell, that is the guy who developed this chart in order to quantify or differentiate color. And to quantify this one, there are three so-called parameters lah. Three parameters that is converted into value. Sometimes it is using simple to represent how intense is the color, and also how does the color looks like. Is it dark, or is it light, or is it intense, or what kind of color is that? So it begins with hue, number one. Now hue is the one that differentiate how a color looks like. Is it going to be yellowish? Is it going to be bluish? That is the difference lah, can be made by hue. So the hue is usually sitting at the edge of the Munsell color chart. So every page, there is a small part at the edge of the page that you can see YR, or maybe some other alphabets. Now YR here means yellowish red. So 2.5. Why is 2.5? Maybe that is number given to the color between red and yellow, maybe a little bit of orange. If it's more red, then probably you have higher number. But I'm not sure if that is the case. But these are the ones that you use. So how the student determine the soil color is that you will need to use a piece of A4 paper, A4 dry A4 paper, and then from the soil sample you put a little bit of moisture so that it looks like a paste, a color with a pasty consistency. Then you smudge it on top of the A4 paper. Then after that, with enough sunlight, with enough lighting, you're going to put this piece of paper behind this so-called Munsell color chart. And Munsell color chart actually have a lot of holes, a lot of perforated pages in which they allow you to see through those holes. And near those holes, there are like the color printed on those pages. So you compare lah. Is it the color that matches the color on the Munsell color chart? If it does, then you choose that page. So you start with hue. Okay, so it begins with hue. Then after that, once you have determined the hue, you already stop at one page. The one page that is like hue 2.5 YR, for example. Then after that, what's next? You will going to determine the lightness or the darkness of the hue. So it's yellow and red. Then sometimes those red, sometimes those yellow may be, lighter, may be darker. So vertically lah, yeah, those value. And the value, the highest is 10, the lowest is 0, where 10 means dark color. Oh wait, 0 is dark color, yeah. 0 is dark color, 10 is white color. More white or more dark, depends on this value. Then finally is the chroma. Chroma signifies the purity of the color. How pure is that color? Not really sure how is that one, but you can see the Munsell color chart yourself. And in the end, once you have everything sorted out, this is how it looks like. So to define or to describe scientifically soil color, it's like as you can see right here, 2.55R that represent the hue, and then the value, okay, the value of YR is the second number slash the chroma, which is the purity of the color. So this is the value that you can see when you define the soil color. Now, where do we go from here? Now, actually, you can actually do, oh, by the way, before that, one soil, one Munsell color chart, you can actually buy from Shopee, and it costs you, listen carefully, yeah, it costs you the same cost can bring you a or very modest motorbike. The Munsell color chart costs as expensive as that. I know it's ridiculous. Munsell color chart is like a book, but it's as expensive as a motorbike. So here's what I want to tell you. Actually, you can use your phone and convert your phone into Munsell color chart. How good is that? Yes, you can. All you need to do is you just need to go to App Store You go to App Store and you can find there are plenty of so-called apps that you can use to find soil color. Yes, just use your smartphone. No need to buy Munsell color chart. You can. Okay, I know you want to find this app, right? Okay, do it later. Do it later. In which at the end of today's lesson, I'm going to brief you also about lab work later, using that app as well later. Yeah. So let's finish. Soil consistency. We're going to continue with consistency, but it's closely related with texture because consistency means how sticky they are. So if you have a lot of clay, then it is higher in consistency, more sticky. Uh, but frankly speaking, I haven't given any one of my previous students about this question at all because frankly speaking, it does not translate into any meaningful information in terms of agriculture and environment. Because yeah, sticky. Then what? Not much we can tell lah. Not much it will help in terms of describing and also help us uh, define the level of pollution. Yeah. The only thing that you have higher consistency is due to the difference in clay content. So, so yeah, apart from clay, high organic content also can cause all those stickiness as well. And of course, it also affected due to the wet and dry soil. So because moisture is there to cause the adhesion, plasticity, stickiness. So I won't going to sit too long on this one. Yeah, I think I find one meaningful word here. You remember earlier when I told you there's a word that people use for a good soil texture and the term is friable. So here is related to consistency lah. Friable means soil materials that can be crushed easily under pressure, low pressure, mind you. Technically, is a soil is termed friable if a soil of 2 cm can be easily crushed between thumb and forefinger. If they can easily crush, that means they have a soft texture, and usually these are caused due to high organic matter. So high organic matter, this is a term that usually people use to define that in terms of their consistency. Dry soil, usually they are very hard. Um, so yeah, as you can see right there. And I think we're nearing to the end of today's lecture. So soil temperature, what is that? Temperature, I'm sure you know what is temperature, but why temperature is so important here? As I told you earlier in the early part of the lecture, too hot, it kills because enzyme denature. Too cold, what happened? It will going to cause cause life form to be dormant, like seeds. If seeds that are like keep in a cool temperature, they're too dormant. Now, why that's the concern? If microbial activity is kept at dormant state due to low temperature, the nutrient will not be recycled. So most of the nutrient in the soil, they are recycled. There is a cycle of nutrient that moves from dead matter to life and life back to dead matter. So the microbes are there to do all the job. Plus the soil organisms, any soil organism, microorganism as part of it, does all this nutrient cycle. So without a proper temperature, this cycle will not move through. I think I explained enough lah. So how does a soil maintain a good soil temperature? Like I told you earlier, must have enough air, must have enough moisture, and moisture alone can actually buffer the sudden change of temperature. Okay? So like I said, microbial process cannot be too cold, cannot be too hot. Too hot, denaturation. Too cold, dormant. Yeah. Um, but of course lah, yeah. So most of this temperature, they affect enzyme and whatnot. Most of the living organism rely on enzyme activity to survive. So anyone an enzyme, if it gets denatured, then trouble comes. Yeah. Okay, so weather patterns. Apart from that, soil color also may also affect a little bit of this temperature. If it's dark, then it absorbs more sunlight. It gets hotter. But mind you, if the soil consists of a lot of sand, the temperature also can get really, really high, even though sand is white color. Because why? Sand do not retain moisture. And then what? If they don't have enough moisture, they don't have the ability to absorb and buffer the sudden change of heat. So another reason why sand cannot be used for planting is because it can get very, very hot because they don't retain moisture. Yeah. Okay, apart from that, if you have high rainfall, high moisture, soil temperature usually low. If you have soil cover, that means the radiation or the sunlight will not go to reach the soil, so they might get cooler. Yeah. And aeration. So as you can see right there, now air involves ventilation of the soil. With gas moving into and out of soil, aeration determines the rate of change. And what does that have to do with the temperature? I would say it won't go into effect with the temperature, but soil aeration is how much of air they can transpire through. It looks very similar to soil permeability. In fact, to me, I don't really see how much of difference except that maybe soil permeability they are used for water, but for air, probably they're going to use soil aeration more than that. Okay, like I said to you, aeration is important because we need air inside to sustain life. Organisms need to survive, and what more? To allow the roots of the plant to conduct respiration during nighttime. So more of that, and I think we are nearing to the end of our lecture. Now, I'm not going to tell you too much about the story of soil aeration, yeah, because if air inside, that means more oxygen, life can be sustained. It probably going to get you more red color from the iron oxide, but that's not our concern. Our concern is aeration is important to allow oxygen to go in to sustain life. However, if there's no air, organisms still can sustain, but they do it anaerobically. But that is bad, lah, yeah. Because if you look carefully at the right hand side, anaerobic organism, the third point, they were going to produce a lot of toxic components like methane and other hydrocarbon gas. I would say not just methane, yeah. If anaerobic organism are going to do all the respiration, they will also produce hydrogen sulfide, ammonia, etc. So hydrogen sulfide and ammonia is when something goes really bad, you close it tight, and then you get all this bad smell, kan? And guess what? These not only bad in terms of their smell, but that can also kill. Yeah, hydrogen sulfide, too stinky, can kill. Yeah, okay. It's not because they are very stinky until they kill, but they are actually toxic. They can kill because they are toxic. Okay, so I repeat again, hydrogen sulfide and ammonia. So now you know why Indah Water people, okay, IWK employees, when they are working, they actually carries what they call air sampler together with them. If the level of ammonia and hydrogen sulfide gets too high, they will beep and they need to escape. So is it good for an aerobic condition to happen? Actually, it's not. It will kill a lot of things, yeah, because of the toxic substance there. Okay, I think I don't want to keep talking about the same thing again. Oxidation, reduction. Things already explained to you. You see, a lot of things has been repeated because if you remember, earlier we talked about permeability, bulk density, and then soil aeration. Balik, it is still the same story, kan? You need a lot of air, you need enough air, you need enough more moisture to flow through, but ultimately it's the same story. So I don't think I need to repeat so many times. And I would say uh, I think I'll skip through lah because what a lot of things I already explained. I know you can read yourself because for the sake of today's lesson and for the sake of uh, your focus, yeah, I think I'll just move through. You will read it yourself. Aeration is still important, but because I've already explained so many times earlier, I think I will not going to repeat myself. And I will go straight to the concluding remarks. So, physical properties. Oops. Physical properties of the soil. Why is so important? Because it's so easily conducted, it's so easy to do, that even a poor farmers can do it by themselves without having to require sophisticated and high technical knowledge to determine that. And for your information, farmers lah, they just use their fingers to measure, I mean, sort of measure the quality of the soil. Yeah, don't need to like send the samples to a lab to determine. You can determine right there, based on the color, based on the texture, and based on, yeah, these two only alone you can already know whether the soil is good or not. Yeah.